11 dash 17. Okay, a refrigerator uses R134A as the working fluid and operates on the ideal vapor compression refrigeration cycle, except for the compression process. Okay, the refrigerant enters the evaporator at 120 kPa with a quality of 34% and leaves the compressor at 70 degrees Celsius. If the compressor consumes 450 watts of power, determine A, the mass flow rate of refrigerant, B, the condenser pressure, and C, the coefficient of performance of the refrigerator. And then they give a schematic, which is the general figure for vapor compression cycle, and then they labeled the information they gave us. All right, so we have the R134A, ideal vapor compression cycle, except, it says, except for the compression process, except for compression process. Okay. Then it says we have the pressure entering the evaporator. So P evap in, it says 120 kPa, and they tell us the quality entering is 34%, 0.34. Okay. Leaves the compressor at 70 degrees Celsius. So we have the temperature of the compressor out, 70 degrees Celsius. And then the compressor consumes 450 watts of power. Okay, so that is our net power in. It's 0.45 kilowatts. Okay. They want us to find part A is a mass flow rate of refrigerant. Part B is the condenser pressure. So the pressure of the condenser. And part C is the coefficient of performance, and it's being operated as a refrigerator, so COPR. All right, our schematic. Our heat exchanger at the bottom. So that's our evaporator. Heat exchanger at the top is our condenser. And we connect them. Okay, so we're entering the compressor, state 1, raising its pressure and temperature. We leave at state 2. Okay. Then we condense it, keeping pressure constant. And that's state 3. Then we go to our expansion valve. Okay, and we drop its pressure, which drops the temperature. And now we have a nice cold temperature where we can go through our evaporator. Okay. So state 4. Okay. So we have heat coming in here. Okay. Coming in our evaporator is our refrigerants at a lower temperature, and we're evaporating that fluid. Condenser, rejecting heat, so we're condensing the fluid, the refrigerant going through it. And then we're putting in work here, right? So there's only work in on the compressor. There's no work out because we have an expansion valve that doesn't have any work. Okay? Assumptions. So every device is one inlet, one outlet, right? But neglecting kinetic energy, potential energy in steady state, right? So where do you want to begin?
Will we start by making one of those state charts?
So the table?
Yeah.
Is that what you meant?
Yeah, sorry.
That's all right. I'm just making sure. So if we have 4 states, so we can have 1, 2, 3, 4. Temperature, pressure, enthalpy, entropy, quality, and specific volume, right? So we got our pretty table now. Okay. They gave us the evaporator in, right? So that would be state 4. So they gave us pressure and quality. So that was 120 kPa and 0.34 quality. So that was our given. And then they also gave us the temperature of the compressor out. So that's 2, right? So this was T2. This is P4. This was quality 4, right? Now we know our cycle. We know how to label it. So 2, we have 70. Okay. So we have that. Is there any other information we know?
Three or 4 H is constant.
So the enthalpy from 3 to 4 is the same, right? Yeah, so we have, it's isenthalpic. So that means state 4 is fixed, right? We have 2 independent intensive properties, pressure and quality. So we can get our enthalpy. means we also get it over here at state 3. Okay. Anything else? Anything else we know? Or where else would we, another step or something would we do to start us down the path of knowing more information?
You would have to draw the TS diagram.
Yeah, the TS diagram. Okay. All right. All right, so we'll start at the inlet to the compressor, so state 1. Okay. We're right here. State 1. Now we go through our compressor. The compressor, it says, is not ideal because it's everything except for the compression process is ideal. Okay, so I'm just gonna put this not like that, or that. That's good enough. All right, so let's say we go like that. Okay. Now we are going through our condenser. We're rejecting heat, so we're dropping an entropy. Our entropy is decreasing, keeping pressure constant. Go all the way and condense it. And we end up at state 3, right? Then we said we have isenthalpic. So we end up at our isenthalpic process, delta H is 0. We end up at 4. And then we go through our evaporator, right? And we evaporate the refrigerant.
How did we know it was isenthalpic again?
The expansion valve. So that's just like from your, it's just like a throttling valve. So a valve, you have, if you put your boundary around the valve, right, there's no work, no heat crossing it, neglect potential energy, and we can actually neglect kinetic energy. So then the only thing you're left is mass flow rate carrying in enthalpy, mass flow rate carrying out enthalpy. So then the mass flow rate's the same. So you can divide out the mass flow rate, so you get that the enthalpy is the same from the inlet to the outlet. Okay, that doesn't change.
Okay.
From the COE. Yep. All right, and then we have our compressor work in there. Okay. What from doing now our TS diagram, going around the diagram. All right, so we got our TS diagram. What else can we do from our diagram into our table now?
You can see that pressure at 1 and 4 are the same.
Okay, so this is our, I'll just call this low pressure. All right, so pressure at 1 and 4 are the same. We have 4. So that means we have 1's pressure. What else?
the quality of 3 and 1.
Yeah, so that's a big one when you're dealing with the vapor compression cycle. So this quality is basically given in this one. So let's do that in a different color. Okay, by being a simple ideal vapor compression cycle. Okay, so we know, and that's really beneficial because it really tells us a lot about our states. It gives us a lot of state information if we can just know that. All right, so now state 1, we know the enthalpy, right? We have 2 independent intensive properties, pressure, so we can get enthalpy there. Okay. So how do we get state 2's information?
We know the work in. Maybe we could use like a, what's it called?
I'm not sure.
I was thinking maybe use like an efficiency, but we don't have that ratio.
Yeah, we don't have the the isentropic efficiency of the compressor. Yeah, we don't have that. So we don't have that. We have the power, but we don't have the work, right, for the compressor. So that means if we did a COE on that, mass flow rate is also an unknown. Any other ideas? Maybe from information from the other states.
Could we get using the H value, could we get the pressure at 3?
Yes. Okay, so that's the key. So we know 2 independent intensive properties at 3. So we know if we needed it, we could get any of those properties then, right from there. State is fixed, right? So we have enthalpy and quality. So we can go to our table and find where 0 quality is, where saturated liquid has that enthalpy. And where that occurs, we actually get a pressure of 799. Okay. And what does that tell us then for 2?
It's the same.
Yeah, so the pressure is the same, right? That's our high pressure here. So 799 or 800 would have been fine to put. So we have our condenser pressure. Okay, so that one was asked. So 2 and 3. So we have that condenser pressure. Okay. And now we can get the enthalpy there. So we have 2 independent intensive properties. State 2 is superheated, so pressure and temperature are independent. So we get 306.92. Okay. So we have all our enthalpies. Now let's look at part A. It's looking for the mass flow rate or refrigerant. Okay. What do we do to get that? Any ideas? All right, we're looking for.
Thinking maybe 3 to 4 could do that because there isn't work out or in.
3 to 4. Yeah. So, but the enthalpy is constant. So the mass flow rate would end up dividing out. So mass flow rate, right? It's a rate, right? So we need to know this is SI units, right? So we have then, you know, kilograms per second. So we need something with a rate. We have a given
work in.
Yeah, so we have, here's kilojoules per second or kilowatts. So we need to use the work in, okay? So that would be, now that we have state 2, because we have the state is fixed at 2, so now we can do our COE here, right? It's an open system component, and it's one inlet, one outlet. I know how much everyone loved the last example that we did in the Rankine cycle or Rankine chapter with all those different inlets and outlets and, you know, dividing mass flow rates. But we just have, in this one, unfortunately, we just have one inlet, one outlet on each device. All right, so with that, with our assumptions of neglecting kinetic and potential energy from our COE of an open system, we can simplify it to this, right? So it's the compressor, so it's adiabatic. And then we can we have work in, and it's mass flow rate at 1, change in enthalpy, right? So if we look at that, we have enthalpy 1. We've already figured out enthalpy 2. We have our power in, right? Right here. So the only unknown then is our mass flow rate. So mass flow rate for 1 is the same as the mass flow rate of refrigerant because it's the same mass flow rate going through all these components, right? Which is solve, we get 0.006 435 kilograms per second. So now we know the mass flow rate of a refrigerant to have that size compressor, right? Because we can have this TS diagram for a small cycle or a very large system, for a small system and a very large system. And the power for the compressor scales it, scales the mass flow rate, scales the system, right? If we want a larger cooling load, we get a larger mass flow rate. Okay? Larger compressor. Any questions so far? I'm going to leave it right there. Okay, we only have one more part, but this is where I ended up stopping in the other class. Okay, so we'll finish part C in next class, and then we'll do another, at least one more example. Okay. Any questions?
So mass flow rate doesn't change because we use the same refrigerant the whole time, or because it was one inlet, one outlet, or both?
Yeah, because they're all one inlet, one outlets, right? So here, if we look at our schematic, right, this is gonna, you know, it's just a tubing, and it goes from this side to this side. From here, it's flowing through, and it goes to this side. Here, we're flowing through here. So it's one inlet. Each device is one inlet, one outlet, and the mass flow rates are all going to be equal, right? Mass flow rate 1 is equal to 2, which is equal to 3, which is equal to 4, right? So it's all the same mass flow rate in this cycle. Where last class we started splitting it and then putting it together. So we had to split the mass flow rate up and then come back. So it was different mass flow rates going through different devices. Okay.
Gotcha.
Professor, I had a quick question.
Mm-hmm.
So how exactly, can you explain to me how exactly the expansion valve, like basically makes it turn into a almost like a mixture?
Yeah, and it's just because it drops pressure. So it's just restricting flow, right? And it drops pressure. So by just from states, information of states, by just dropping pressure, right, we drop the temperature also, okay? So it's all based upon states here. Because the enthalpy is the same, we go over here. If we were going through a turbine, we had a turbine that could handle that, a mixture, we would end up like here, and we'd be at 4 prime, like this location right here, a nice entropic turbine. But turbines can't really handle that mixture, so we use an expansion valve, which is basically just like a throttling valve, and we end up constant enthalpy, and that takes us to the right. They have the same enthalpy as 3. We end up at this location at this lower pressure.
And in real life, like a real life application, would that expansion valve like require any work input, or is it just?
No, it's just restricting. So it's just small orifice. Just think about it as just a drop, like a valve or a valve, right? In reality, expansion valve usually controls the amount of that orifice because it kind of regulates the flow. So it might have the temperature gauge connected to the valve and open and close itself to allow more or less. But it's basically just a restriction. Like think of a very simple one was shown in the slides. Let's say you have a pipe like this, but then you put it into this like teeny tiny pipe. Like think of, you could put it into like a size that like a needle has. Like think of like a needle that you get your flu shot with or something, right? Think how much, if you're doing that pushing, like if you had a plunger system, how much you have to push in that plunger to get that flow rate, right? You're dropping that pressure because of that, right? And you're dropping that pressure, it's restricting the flow so much, it's dropping pressure. So you get a lower pressure over here than here, okay? Because of all that restriction that you have, right? So you drop pressure, and because of that drop in pressure, while keeping the enthalpy the same, right? Then we have a lower temperature. So it has to drop in temperature. If it didn't, like let's say, we'll talk about this in chapter 12. Hydrogen, I think it's hydrogen, or is it helium? One of those, depending upon what temperature you're at, will increase in temperature when you drop pressure versus decrease. So then it doesn't work well as a refrigerant at those ranges. Okay. So you want, when you drop pressure, you want it to be a fluid that drops temperature also.
And would that like a valve be like something that absorbs heat as well? Like how does it not absorb the heat? I mean,
you could,
like you do have like a heat loss, but like it's just neglectable.
Yeah, so everything, like most of the time, yeah, you could have it insulated or whatever. I mean, everything has some kind of heat loss throughout this whole system, right? But it's just small compared to the other energy transfers. Yeah. Right? Because you feel it, it's going to feel cold, right? Or so, you put your hands on it, it's going to feel cold, but it's going to be negligible compared to the enthalpy change. Not enthalpy change, but compared to enthalpy is U plus PV, right? And here it's U plus PV. And by enthalpy being constant, that means these terms change from here to here, the quantities. and that results your internal energy and flow work. The enthalpies are the same, but internal energies and the flow work change from 3 to 4.
Let's see. Okay. Thank you so much.
Yeah,
You have a good day.
you too. You guys have a good one. See you on Monday. Good luck on your exams. I heard you guys got a bunch of them.
Next week.
Yeah.
All right, have a good one, Professor.